Okay, welcome to lesson 2 from chapter 6, Pure Mathematics. This is Trigonometric Functions from year 2. And today we're going to look at the graphs of sec, cosec, and cot. I've given them their full names here, secant, cosecant, and cotangent. So previously we saw how they are represented geometrically, how they are related to sine, cos, and tan, as they're reciprocals of sine, cos, and tan. And we also saw some new identities, the Pythagorean identities. Now, today we're going to look specifically at the graphs. Okay, so it's going to feature a little bit of work on transformations that you've done many times previously. So please pause the video, and if you have a go at the 4 warm-up questions, and then I'll go through them with you momentarily. Okay, and let's have a look at the solutions. All right, so question 1 is relatively straightforward. We just have to substitute in these particular values of n here into the expression provided. Okay, let's see what happens if we do that. So the first value of n is obviously -1. So when n is equal to -1, what do we get? Well, we're going to get 2 multiplied by the -1 if I substitute that in. Then I have to obviously add 1 to that, divide by 2, and this is multiplying pi. Okay, so we have -2, add 1, which is -1. So it's going to be -pi over 2. All right. So assuming this is a radians measure, this would be like -90 degrees. Let's move on to the next one, which is n equals 0. So this time we're going to have 2 multiplied by 0. We're going to add 1. And we're also going to divide by 2, and that's again multiplying pi. Now that means that we're going to have pi over 2. Okay, or 90 degrees. Okay, so it looks like it's increased by pi. So as n is increased by 1, these terms here, if you think of it like a sequence perhaps, we've added pi here. Okay, so there's a couple more to do. So when n is equal to 1, sub that in. So we have 2 multiplying 1, add 1, divide by 2, multiplying by pi, and that's going to be 3 pi over 2. So it looks like the trend is continuing. We're adding another pi to that. And the final one, when n equals 2, we have 2 multiplying the 2, which we sub in, add 1, divide everything by 2, multiply by pi, and we get 5 pi over 2. Okay, so we get half multiples of pi, and you can see clearly n is increasing by 1 each time, so we're adding pi here. Okay, and we're adding pi here. We're 2 pi over 2 essentially. Okay, so that's just so you can see, as awkward as this looks, when you start subbing in values of n, natural numbers, remember, n usually represents natural numbers, we get quite a nice sequence increasing by pi each time on the halves. For question 2, I've just added the x and y axes onto the diagram. Notice the domain here, we're extending from -pi up to 2 pi in the x direction. Obviously, that's what I meant by the domain. So we've done that on the graph here. It should just fit on nicely if you do that. We're looking at sine x, sorry, I beg your pardon, sine 2x. Now, if you remember from your work on transformations, the sine 2x, obviously, this is a transformation in the x direction because the transformation is inside the function. And it does the opposite to what you'd expect. Okay, so rather than doubling the x values, we're going to multiply the x values by a scale factor of 1/2. Okay, so it acts as a squeeze in the x direction. The y direction does not change. Okay, so that means that I can allow my y values, my range, to span between -1 and 1. So we just have to draw this. Now, I'll draw sine x first, just to show how that looks, and then we can add sine of 2x over the top. So sine x is something you should be familiar with. If I start at 0 and go right, first of all, so it maxes at pi over 2, minimizes at 3 pi over 2, and that's the sine wave. And if I just continue in the negative direction, we have the same thing. That's not too bad, is it? So that would be y equals sine x. Okay, so for y equals sine 2x, which we have up here, we have to halve all the x values. Okay, so the x-intercept at pi is now going to be at pi over 2. Okay, but the range doesn't change. So that means that my sine 2x, I'll do this in red, is going to max out at pi over 4, like so. And it cuts the x-axis now at pi over 2. And if I just continue that. Okay, so we've doubled the period. Okay, so just to check this, we remember in sine x, we had an x-intercept at 2 pi. That's now been halved to pi. Okay, and if we just carry this on in the negative direction, same thing's going to apply here. Okay, so by putting the 2 inside the function, multiplying x, we double the period. Okay, so the graph repeats itself twice as frequently as sine x. All right, for question 3, I've had to zoom out a little bit. What I've put on the axes so far, I've put the axes on the board from -2 pi up to 2 pi inclusive, and I've sketched the graph of y equals tan x. Now, that's not obviously the objective. The objective is to sketch tan of x plus pi over 2. So we need to have a little think about what this transformation actually means. Again, the transformation is inside the function. It's inside the bracket here. So it's going to affect the x coordinates only. There is no y transformation at all. And this means that it's going to be a shift in the supposedly the opposite direction to what you would expect. Okay, so it looks like we're going to have to move the graph of y equals tan x to the left by pi over 2. Okay, now I can do this relatively straightforwardly on the board. Notice I've got the asymptotes there as vertical straight lines. So we're going to move the entire graph pi over 2 to the left. So if I do that, now this one is going to fall off screen, so I can actually remove that in a moment. In fact, I'll do that now. So this one's gone. This asymptote is currently at -3 pi over 2. So if I move that pi over 2 to the left, that's going to end up there. If I take the tan x curve, I'm going to move that to the middle here. And same with all these, so from -pi over 2 to -pi. I can move this tan curve from an x-intercept at 0 to an x-intercept at -pi over 2. And I can keep doing this. So I've got an asymptote at x equals 0, another x-intercept at x equals pi over 2, an asymptote at pi, and if I move that half branch, now what I'm going to have to do is just add a little bit more to this, like so. Okay, so now we have the graph, and I'm just so we avoid confusion, I'm going to rewrite this right here. So that's going to be y equals tan of x added to pi over 2. All right, so it's just it's a simple transformation. It's just obviously you've got to have some knowledge of the tan graph. Question 4 is yet another sketch. This time we're sketching for the domain negative pi up to 2 pi inclusive for theta. We can see this on the graph here, and notice I've sort of preempted what's going to happen here. We don't have the x-axis in the center, and what I've done is I've sketched the graph of y equals cos theta, so you can see that. Now, if you notice that we have a +1 added to our function here, and what that means is, of course, it's a y transformation. It's outside of the function. It's not a cos of theta +1 inside the function. It's outside. So this is a y transformation, and we're going to transform vertically. It's a translation, and we're going to move the graph 1 unit upwards. Okay, which is essentially what that means. It's your job to interpret what the function is telling you to do. If it's a transformation of a parent function like cos, and there's some coefficients in there or some extra terms, you've got to know what that means when you're transforming your graph. So I know I have to move this up one space. So I can do that hopefully relatively straightforwardly. I'm just going to drag this and move it one place up. It's in 2 pieces. Okay, and now I can adapt my graph. It's not the best graph I've ever drawn, but it should be. In fact, let's make sure it should touch the x-axis there, shouldn't it? Okay, there we go. It's not too bad, I suppose. So let's just relabel that. So we've now drawn the graph by moving everything 1 unit upwards. We now got the graph of 1 add cos theta, okay, as required. Now, for part B, you're using your previous sketches. Now, I've had to erase my previous sketches to make sure these all fit on the screen. We talked a bit about the range of sine of 2x here. We know because this is an x transformation. All right, now just to reiterate this, there's a transformation in the x direction, and in the same way in the third graph here, x plus pi over 2. The domain is different in each case, but because these are x transformations, we know that the range does not change from the parent function. So I know I'm in the first graph, as long as I know what the range of sine x is, then I've got my answer, because the transformation does not affect the y direction. So I just write it in, don't I? So the range is just going to be the normal sine range, which is anything between -1 and 1 inclusive. I'll go on to the third graph, because if you know the range for tan, we know tan can take any real number. It's the domain that is a problem for tan when you have the asymptotes. Okay, now the only one I have to consider as an adjustment is the third one. Now that luckily we've got that staring at us, haven't we? Okay, remember the original, I just write it in for y. If it was y equals cos theta like that, we know that cos theta itself is bounded between -1 and 1 in the same way as sine is. If I add 1 to that, okay, I've got to add 1 to each of my range values here. So I've got to add 1 to this and add 1 to this. Okay, which would give us the following. So this would give us 0, add 1 to that, and then up to 2. So my range is simply going to be here anything between 0 and 2. And you can see that from the graph. We've just sketched it. It's staring at you. So it should be pretty obvious. The graph is only valid between y values of 0 and 2. Okay, and that concludes the warm-up. So the idea of this lesson is to really get to grips with the graphs of the 3 new trig ratios, sec, cosec, and cot. We're going to start with the graph sec x. And I haven't specified a domain here, but what I have done is I've added the axes to the grid already. So I'd like you to do the same on your notes and or on a piece of paper. And we're just going to specify the domain, okay? And we're going to make the domain as large as possible. That will mean that you can see the behavior of the graph in a bit more detail. So if we just, oops, I didn't want to do that. Let me just undo it. I've just erased my axes. So we'll put some notches here, like so. And as is sort of typical with trig graphs, we can go up in multiples of pi, but because we've got such a broad range here, I shouldn't say range, but because we've got such a broad domain here, we can go up in pi over 2. So if I start on the right-hand side, pi over 2, and keep adding pi over 2 to each one. So pi, 3 pi over 2, 2 pi, okay? And in the negative direction, we'll have negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, we'll leave it like that. So we'll sketch the graph between negative 2 pi and 2 pi. So let's just specify that on here. So we'll have a domain from negative 2 pi up to 2 pi. Now, I'm going to make this a bit more interactive here. I'm going to show you what it is I'd like you to do next. Now, we're going to put the Y scale on now, and I'm going to put 1 and negative 1 like that. Okay. Now, what I'd like you to do first, and I want you to pause the video at this point, I would like you on the axes to sketch the graph of y equals cos x. I'll write that down. So can you sketch y equals cos x? All right, so pause the video and do that, and then we will continue. All right, so now I've added the graph of y equals cos x to the diagram, okay? And it doesn't look like I've made the best use of space, does it? But there's a reason for this. Now, why cos x? Well, the first reason, obviously, is because cos and sec are reciprocals, as you remember from the previous lesson. So we know, I'm just going to write this up here. We know that, just undo that, sorry, I meant to write sec. So we know that sec theta is the same as 1 over cos theta, or sec x is the same as 1 over cos x. It doesn't matter. So they are reciprocal. Now, I'm going to give you a chance to have a go at this yourself. We're going to sketch the graph of sec x, and we're going to superimpose it onto what we've already done. So we're not going to erase this cosine graph. We're going to use it as a guide. Okay. Now, think about what I've just said. This is really important information. Sec and cos are reciprocals. Okay, so you might want to just grab your calculator and maybe put some numbers in. Okay, set it to radians, put some numbers in, and think about what would the graph of 1 over cos x look like. Okay, so again, pause the video and maybe sketch this perhaps in light pencil. So in case you make a mistake, we can come back to it, and then we'll talk through the thinking process. Okay, so pause the video now, and then we will discuss how to draw the graph. All right, so now you've had a little think about that. Hopefully you've got some results there that you are happy with. Now, we could do this in a systematized way. If I want to draw the graph of y equals sec x, I've got to be thinking really about 1 over cos x, because they are reciprocal. This is the important relationship here. And looking at the graph we've got already of y equals cos x, we've got some sort of key nodes here. Now, I'm going to start looking, first of all, at the zeros, where cosine crosses the x-axis. Now, if we think about what's going on here, the cos value at each of these is worth 0. Okay, I think we can agree upon that. So for example, if I take the cosine of pi over 2, okay, that's equal to 0. The cosine of 3 pi over 2 is equal to 0, and so on and so on. Now, if that's reciprocated, then I have to write 1 over the cosine of pi over 2, which is 1 over 0, or 1 over the cosine of 3 pi over 2, which is also 1 over 0. Now, 1 over 0 is a problem, okay? It isn't undefined. It's sometimes sort of addressed as infinity. It's not really, it's undefined. It's not a real number whatsoever. So that means that we can't plot the graph at these nodes, okay? These nodes, we cannot plot the graph. So how do we represent that? If we're asked to sketch this, what are we going to do? Well, we have to put asymptotes in here. So that's what I'm going to do. So we're going to put some vertical asymptotes in along at those nodes. So I'll do those in orange. Okay, you probably should use a dotted line for this. I don't have a dotted line function on here. Okay, so these are the asymptotes. So I'm going to add them to my diagram. So wherever the cosine graph is cutting the x-axis, intersecting the x-axis, we know that the graph of sec is going to be an asymptote because 1 over 0 is not defined. Okay, so just make a note of that. These are asymptotes. All right. Now, what are the other important points on the cosine graph? Well, the maxima and minima spring to mind, don't they? Okay, we have maxima and minima all the way along. So we have a minimum point there, maximum point, a minimum point, a maximum, and so on and so on. So let's consider what happens at these maxima and minima. Well, if I take the cosine, again, I'll just do some notes over here. If I take the cosine of 0, for example, okay, in radians, I know, or in degrees, we know this is just going to be 1. All right, now if I reciprocate that, 1 over cos 0 is just going to be 1 over 1, which is 1. It's the same, it doesn't change. So I know on my sec graph that this point here, which I'm just marking with an X, must be on the sec graph. Okay, because 1 over 1 doesn't change. Now we have another maximum over here, so that's going to be the same thing. If I take the cosine of 2 pi, we know that that is equal to 1, and if I reciprocate 1, I just get 1. So we're actually making some progress here, and then we've got also the negative 2 pi over here, which I shouldn't forget about. That's also going to remain the same, okay? These points coincide. So we've now got some asymptotes, and we've got some points that are definitely on the graph y equals sec x. So now let's have a look at the minimum points now. So we'll do these, I'll do these in a different color. We'll do these in pink. So we've got minimum points at negative pi, pi, and whatever else if we extended the domain. Now, if I consider what happens when I do the cosine of negative pi, okay, well, we know we're going to get negative 1 for that. Now, if I reciprocate negative 1, again, it remains unchanged, doesn't it? It's going to be 1 over negative 1, which is just negative 1. So this point here is going to remain unchanged. And without doing too much more, if I take the cosine of pi, which is negative 1, and reciprocate that, I'm going to get negative 1. So we now have some points that are definitely on the sec curve. The question is, what is happening in between? Now, I'm going to give you, I know you've already had a go at this. If you've not done it quite right, I'm going to give you a minute or two. Just pause the video and rethink what's going on here, okay? And then we'll come back. All right, now we're ready to sort of finish this graph off. Now we've got these key points here. We've got the asymptotes. Now we need to know what's happening in between these vital points. Now, one way you can do this, if you're not kind of convinced with how this graph's behaving, is to put in some numbers. So if I just grab the calculator, make sure your calculator is set to radians here. So if you don't know how to do that, it's shift menu. So in other words, setup, select angle unit option 2, and again, select option 2 again for radians. So now my calculator is set to radians. And let's have a look at some small values around 0. Okay, so maybe around here. All right, let's see what's going on. Well, if I put in the cosine of, let's say, a small number such as 0.1, and this is in radians, so that's okay. Okay, I get a small number. It's 0.99. Okay, now if I inverse that, or I shouldn't say inverse, if I reciprocate that, so 1 divided by the answer, I get 1. So it's actually pretty close to where I've marked the X, but it's slightly higher. Okay, so that's not telling me much really. It just tells me that maybe it's moving in the upwards direction. So let's go a bit further out. Let's go a bit closer towards pi over 2. Now, pi over 2 is, of course, about 1.57. So if I put 1 in, just cancel that. Let's do the cosine of 1. Okay, now that's about 0.5. Now, and if I reciprocate that, so if I do 1 divided by the answer, I get 1.85. So it appears to be moving upwards. Okay, so I can confidently add to the graph the fact that this is going to be curving upwards. Okay, so I'm going to do that. And it's going to approach the asymptote, but it can never get there. So it's going to start to accelerate up like that. Okay, let's try some negative corresponding values. So if I go back to my calculator here, let's go back to 1. Let's do the cosine of negative 1, for example. Okay, now I get exactly the same value. Now, if I reciprocate that, I get the same values I got before. So 1 divided by answer, 1.85, close to 2. So it's behaving in the same way. So it's a mirror image. So on the left-hand side, between 0 and the asymptote, sorry, I'm just going to redo that. Get rid of that. It's going to be doing this. Okay, so it looks kind of odd. It's sort of balancing on the cosine graph. All right, now, if this is behaving in the same way throughout, all right, again, I can test some numbers. What's going to happen at pi? Okay, well, we know when we do the cosine of pi, it's -1. But what about if we choose a value somewhere between pi over 2 and pi? So, for example, 3. Let's go back to the calculator. So if I do the cosine of 3, so get -0.98. If I reciprocate that, so 1 divided by the answer, I get -1.01. So it appears to be getting smaller. Okay, less. So it seems to be going in the opposite direction. Okay, now I can add that to my graph. Like so. So it's going to be doing this. Now, with a little bit more checking, putting some values in, what you'll notice is between pi and 3 pi over 2, it's going to behave in exactly the same way. And also between -pi and -3 pi over 2, it's going to be behaving in the same way. If I move over to 2 pi, it behaves the same way as it does around the 0 mark. All right, so we've actually got a reasonable sketch there. We just got to finish it off. We've still got some domain unaccounted for over on the left. So this is going to go like that. So it's an unusual looking sketch. All right, but if you can sketch the cosine graph, the simple summary is put the asymptotes where the cosine graph intersects the x-axis, and then use the maxima and minima to draw the curves. Okay, so for the maximum points on the cosine graph, the sec graph is curving upwards, and for the minima on the cosine graph, the sec graph is curving downwards. So the maxima and minima are inverted. Okay, so I think that will conclude the sketch for y equals sec x. All right, next we're going to look at the graph of cosec x. And as you can see, I've just added the axes and labeled them. We're going to look at the same domain as last time, from negative 2 pi up to and including 2 pi. I'm just going to finish labeling the y-axis now. Okay, so just to specify the domain here, it's not specified on here, but we'll just add it anyway. So the domain, we're going to look between negative 2 pi and up to and including 2 pi. Okay, now as you can see, the scale on the y-axis, at the moment, I'm just interested in all values between -1 and 1. Okay, and you'll see the reason for this in a moment. Now, to look at the graph of cosec x, we need to consider the reciprocal of this. Now, remember the reciprocal, we use that third letter rule. Okay, if we look at the third letter, it's of course s. So we'll just make a note. This is important information. So if I'm interested in the graph of cosec theta or cosec x, it doesn't really matter. I know it's the same as the reciprocal of, now the third letter is s, so that's going to be sine theta. So that's the way to remember it. Okay, that's really important information there. So make that look important. Add that to your notes, like so. Just making that look important there. So we need to consider, first of all, the graph of sine theta. So what I would like you to do, just pause the video and add to the axes that you've drawn, the same as mine on the screen here, add the graph of y equals sine x first. Okay, and then we can talk about cosec x. All right, so I've just added the graph of y equals sine x in purple onto the axes there. So we're going to consider the reciprocal of this. Now, as we learned in the previous example, we can first look at these nodes where the graph intersects the x-axis. So I'm going to highlight those, okay, and we can consider what happens at these particular points. So remember, of course, that sine x is equal to 0 at these points. Okay, and I'm not going to labor this too much, but I just want to make the point that if we look at these values, so if I consider sine of 0 radians, of course, the answer is 0, isn't it? It's, if I consider the sine of pi, which is 180 degrees, that's also 0. And if I reciprocate 0, 1 over 0 is undefined. Okay, so it's the same idea as with sec x. It's going to be an asymptote at these points. So we can add asymptotes at these nodes here. So I'm going to do that. So you can maybe use a dotted line for yours. Okay, and then there's one on the y-axis there. All right, and I'm trying to do this as carefully as I can, and that's in the domain, so I'm going to put that asymptote on there as well. So we've got asymptotes. We also need to consider what happens at the maxima and minima. So there was interesting behavior at those points as well. So we've got maxima. I'll just undo that. Let's use the highlighter instead. So we've got maximums here and here. Now, remember, of course, if I take the sine of pi over 2 and the sine of negative 3 pi over 2, I'll just make a note. I'm going to get 1. Pi over 2 is 1. And the sine of negative 3 pi over 2 is also 1. So once again, these points are not going to change. They're going to coincide with the cosec graph. So I'm going to put little crosses there. Okay. at those points. So they're going to also feature on the cosec graph. And without going through the whole thing again, we'll also be able to deduce, you can check this for yourself, that if I take the sine of negative pi over 2, you will get -1. If you reciprocate -1, you will still get -1. And the same thing with 3 pi over 2, the sine of that is -1. The reciprocal of -1 is -1. All right, and we seem to have a very similar looking graph, don't we? Now, just to fill in what's going to happen, the maxima and minima are going to be inverted because it's a reciprocal. So I'm now going to get this kind of asymptotic behavior between 0 and pi, like so. I'm going to be changing from a minimum to a maximum between pi and 2 pi. Same story between negative pi and 0. These are asymptotes, of course, so the graph never actually touches them. And between negative 2 pi and negative pi. So the red graph, this is going to be y equals cosec x. All right. And you can probably deduce now that cosec and sec are related by some kind of transformation. So I'll leave that as an open question, just sort of hanging there, and you can decide what the transformation might be. All right, and the last graph we're going to look at is, of course, cot x. And we know, obviously, by process of elimination, this is the reciprocal of tan x. Okay, so we'll just, again, make a note of what we should be thinking about here. So we know that cot, we'll say cot theta, a general case, is identical to 1 over tan theta. So remember, it's not an inverse, it's a reciprocal 1 over. Okay. Now then, first of all, let's explore the tan graph. Okay, we've got a domain going from, again, negative 2 pi here up to 2 pi. Let's just state that before we press on. So the domain negative 2 pi up to and including 2 pi, just so we can see as much of the behavior as of the curve as possible. So once again, pause the video, please, and have a go at drawing the function y equals tan x for this domain. Now, in the case of this tan graph, that should look something like this on your axes. We've got a slightly different situation, but the principle is the same. We've got to explore these important nodes, in particular where the tan graph crosses the x-axis, because we know the value of tan is 0 at those points. So that's the first port of call. We're going to highlight, so the first one, negative 2 pi, negative pi, 0, pi, and 2 pi, once again. So we know that the tan graph is going to is 0 at those points. Now, if we just make a little note of what's going on here, and then we can decide what's happening with the cot graph. If I take tan of, and again, I won't labor this too much, tan of pi, for example, we know that's equal to 0. Okay, and if I reciprocate that, if I find the cots of pi, that must be 1 over 0. Okay, which is undefined. That means that this is the same place as before, where we're going to have asymptotes. Now, we know that tan already has asymptotes, doesn't it? Okay, at multiples of pi over 2. So it's a case of perhaps there's more asymptotes, or the asymptotes are going to shift somewhat. So what we can do is we can add new asymptotes on these nodes, and we'll see what's going to happen. All right, so what I've done is I've removed the asymptotes from the tan graph, and I've added the new asymptotes, which should be where that should describe our COT graph, particularly at these nodes. All right, I've just removed them just because otherwise the image will get too confusing. So the red asymptotes belong to y equals cot(x), or so we think at this stage. Now the question is now, what is going to happen at the original asymptotes? Now I've removed them, but we know from previous experience that if you see how the graph for y equals tan x shoots to positive infinity and negative infinity at negative 3 pi over 2, at negative pi over 2, at pi over 2, and 3 pi over 2. That's where the original asymptotes were. Now, this is where we're going to have to use a bit of license. If we assume that these values are going to shoot off to infinity, then what is the reciprocal of infinity? We've got to consider that. Okay, now it's probably better to think of it as a really, really big number. Okay, I don't like talking about infinity too much because you start using sophistry. It's not mathematics. Okay, infinity is not a number. It just represents an unending sequence of numbers. So what we can do is we can say, well, what would happen if I put in a value of tan x, for example, and let's use pi over 2 for this one because it's the simplest one. Let's choose a value very, very, very close, but slightly less than pi over 2. Now that's going to generate a very, very, very big y value, okay, that we would read off somewhere way, way up there, and it's going to be a really big number. Okay, now you'll know this from experience. Just get rid of that. If you have a really, really big number and you reciprocate it, what happens? Well, we can try it out. So let's just get our calculator out. So if I just put in a really big number and reciprocate it, so let's say 1 divided by 1,000,000, you're going to get 1,000,000th, of course, which is 1 times 10 to the negative 6. It's a very, very small number. Okay, and similarly, if I take a value that just slightly greater than pi over 2, okay, on this graph, I'm going to get a y value that is very, very negative indeed. It's going to be all the way down here, and I'm going to be reading off the graph somewhere way down here. Now, perhaps it's the same value, but with a negative sign. But the point is, it's going to generate an incredibly small but negative number. Okay, so on the COT graph, if I take an x value just slightly less than pi over 2, somewhere there, it's going to be the reciprocal of a very, very large number, which is going to be a very, very small number, perhaps something there. And if I take a number slightly bigger than pi over 2, find the tan of it, and then reciprocate it, I'm going to get a negative number, but very small. So what seems to be happening is we have the intersection is going from positive through to negative. So it looks like it's decreasing. It has a decreasing gradient. Okay, so let's explore some more values. Well, what happens if we go closer to 0? So in this direction, okay, and a positive number. So if I put in a positive number very close to 0 and reciprocate it, so let's just go back to the mouse settings. So 1 divided by, let's say, a really small number. It's going to be a large number, isn't it? So I've done 1 divided by 0.0001. I get 10,000. It's an enormous number. So that means that if I put in a very small number for x, I'm going to get a very large number for cot. So it's going to be somewhere up here. Now you can probably see the behavior now. So let's plot this. Well, not plot it, it's an approximation, isn't it? But we can see it's going to be behaving like this. Okay, so there's the first cot wave. All right, and just to make things a little bit easier, let's remove these tan curves. Okay, so that appears to be the shape of the cot graph in the interval between 0 and pi, but not including 0 or pi. Well, you can inspect this yourself, but you can take my word for it. If we continue in the same vein and inspect a few more values, you'll notice that this is a repeating pattern. Okay, and you can try this on Desmos or GeoGebra if you want to. So it's going to repeat as these trig functions invariably do. All right, and if I move over to the left-hand side of 0, okay, we're going to have the same repeat pattern going here through negative pi over 2. And I'll just remove the calculator, so let's go back onto here. Just erase that. We can put on the last wave, so it's going to go, oops, I didn't want to do that, just erased it. Okay, so I hope that convinced you. So this is the cot graph. I'm not drawing it particularly well. Do inspect this or have a look at it on GeoGebra and try it for yourself. Now for the worked examples, what I've done is I've taken a screenshot from GeoGebra of the graph y equals cosec. So I'll just make a note of this because this is a strategy I strongly recommend you follow. It just makes life a little bit easier, I think, when you're sketching transformations, which is essentially what we're going to do. So, so first thing, sketch. We'll call it the parent function. Okay, parent function as in a standard function that has not been transformed. And I think we can consider y equals cosec now as a parent function because we've examined why it has its shape and what the shape actually is. And remember, of course, we're only interested in the values between negative pi and pi, like that. So hence I'm going from negative pi to pi there. So that's all okay. We've sketched the parent function. That's what we have on the screen in front of us. We've got asymptotes at negative pi, 0, and pi. And I'm just going to label that just so we're clear. So this is the graph of y equals cot x. Okay. Now, next thing to do, we're going to sketch the transformation. And we'll do this on the same axes. You can always erase the parent function. Okay, but I think having them both on the same axes is a good guide. On the same axes. All right. So we have to consider what is the transformation. Well, the graph we have to sketch in this example is y equals negative cot x. So we'll just have to review what's going on here. Fundamentally, if we know what cot x looks like, which we do, we can sketch this. So it looks like we've got a negative on the outside of the function. So this is going to be affecting the y coordinates. So we can discern that straight away. It's a transformation in the y direction. And we're going to multiply all the y coordinates by -1. Okay, so all the positive y coordinates will instantly become negative, and all the negative y coordinates will instantly become positive. Now, there's an optical effect of this because obviously if you do that, it will look as though the graph is rotating about the x-axis. Okay, so we'll sketch this over the top. So all my negative values on this graph are going to instantly become positive and vice versa. So if we start with what's going to happen here, we'll start in this corner here. Well, that's a very, very positive number, isn't it? Okay, it's just beyond 4, okay, just before we get to negative pi. So that's going to be the mirror image is going to be down here. and then it's going to be the same all the way along. So if we just do a mirror image of this graph through there, that looks like we've got negative cosec, or the first branch of it anyway. So if you're not happy with that, just tilt your head and do a mirror image in the x-axis essentially. Okay, and then we do the same thing on the right-hand side of 0, the positive numbers. So it's going to do something like that. Okay, and we've now got the graph of y is equal to negative cot x. Okay, I hope that was all right. Now, we also have to sketch the graph of sine 2x. Now, this was a warm-up exercise, okay? Sine x we're familiar with. It has a period of 360. It's 0. It has a value of 0 at 0 pi and negative pi. So if we take the sine of 2x, as we saw, it's a compression in the x direction. And I'll draw this in pink. And it's got a range between -1 and 1. So in fact, I'll put that on first. So this is the range of sine 2x. So let's add it to the diagram. Now, originally, sine x would max at pi over 2, but because everything is being halved in the x direction, it's now going to max at pi over 4, and it's going to cross the x-axis at pi over 2. So it's going to behave more like this now. Like so. Okay. Remember, we're only going from 0 to pi. So because the period is doubled, it looks like I've drawn the ordinary sine wave, but that's not what's happening. And then for the negative branch, it's going to do that. I hope that's not too bad. Okay, so we've now got y is equal to sine 2x. You'll have the advantage, of course, of looking back at your solution to the warm-up question. All right, now that's all rather confusing. Let's just add some axes, and then I can erase my original screenshot from GeoGebra. So I think I'm going to do that. So let's just add the axes. So we've got to put the y-axis on there. We'll put the x-axis on there like that. And all right, there we go. So we've erased that image. So let's just complete the sketch. I'm just going to add the labels. X, there's 0, and there's y. We don't have cosec anymore. So that seems reasonable. I think we've got a decent sketch there. Also, you can put the asymptotes on. We are including negative pi and pi, so maybe add those. So 1 at x equals 0, 1 at x equals pi. Just a little bit off there, aren't I? It's a bit better. Okay, and 1 over here. It's a bit wonky, but that'll do. Okay, so there's our sketch. We have to answer a question. So this is the bit where you need to understand what this is telling you essentially. It says, hence deduce the number of solutions of the equation sine of 2x plus cot x is equal to 0. Right. So what is this saying? Well, if we rearrange this a little bit, it looks like a difficult equation. I mean, how are we supposed to do this? Well, the thing that gets people sort of riled up a little bit with these questions is that they're not reading the question. We only have to find the number of solutions. We don't have to solve it. We just have to find the number of solutions. So what we can do, I'm just going to write this down here. So what I can do is I can rearrange this. I can say, well, if sine of 2x added to cot x is equal to 0, then I can put sine of 2x equal to negative cot x. All right. Now, sine of 2x, of course, is my pink graph. Okay. And cot or negative cot x is my green graph. So I just have to find out, when does my green curve and my pink curve coincide? All right. Well, we just have to look at the diagram, and we've got a nice sketch in front of us. So it looks like, now we have to be careful here because we have asymptotes. Now the asymptotes are undefined for negative cot x, so we can't include those, but we can include the curve negative cot x between the asymptotes. So we have a point of intersection there at 0 when both functions equal to 0, and we have another point of intersection there. What we don't have, and I'm just going to stress this now, this is not a point of intersection here because that's where the asymptote coincides with sine 2x. Similarly here, this is not a point of intersection, okay, and neither is this. All right, so the points of intersection are here and here. All right, and we can actually specify what those points are, but we don't need to do that. We can just say the number of solutions. Okay, so there are 2 solutions. And bear in mind, that's only in the interval negative pi up to pi inclusive. So we have to state that. I mean, have a think about how many solutions there would be if we included all real numbers of x. All real values of x, I should say. Okay, so it's just the two solutions for that. So for the second worked example, again, we're looking at the domain from negative pi to pi, as you can see here. So that's what I've taken from GeoGebra. So this is the sketch of the parent function, cosec x. So I'm just going to label that. Okay, so that's what we have on the screen at the moment. That's the first part, is to obviously sketch the parent function as we specified earlier. And we're going to have a look at the transformation. Now, if we look at y equals 0.5 cosec 2x, well, there's a bit of a process here. Let's look at the first transformation. Now, there is an order to doing the transformations. So what we need to look at first is y equals cosec of 2x. So think of the transformations as nested. Okay, start with the x transformations first. It's actually starts off with translations in the x direction, then moving on to scaling in the x direction, and then the y transformations are the final ones you do, concluding, of course, with a vertical translation. So do the cosec 2x transformation first. So we need to consider what's happening with this. So what does this 2x do to our function? Okay, irrespective of whatever function it is, if you put a 2 in front of the x inside the function, it's going to change how it looks. Okay, well, first of all, I've already alluded to this. Which direction is affected? Okay, well, this is an x transformation, so it's in the x direction only. Okay, and we know it's inside opposite because it's inside the function, this transformation. So we're going to multiply all our x coordinates by 1/2. Okay, the reciprocal of 2. So how does this transfer to our diagram that we've got here? Well, let's start with the asymptotes. They're usually pretty easy to start with. If I want to halve my x coordinates, that means the asymptotes are now going to be at 1/2 pi and negative 1/2 pi, because we need to divide pi by 2 and negative pi by 2. So it's the squeezing effect in the x direction. So if I put the asymptote here like this, and the second asymptote here, that's squeezed my asymptotes by a scale factor of 1/2. Now, there's also a third asymptote here. Now, obviously, if the asymptote is at x equals 0, half of 0 is just 0. So you can see how these corridors where the curves appear are now shrunk. All right. And we also know, because this is just an x transformation, the y coordinates are not affected by this. So I can now add the curves. So the y coordinates are going to remain as a minimum at 1 there, and we're going to have a maximum there at -1. So if I put these curves in like so, it's going to look something like that. And the period has been doubled. So I now have to also put in 2 more iterations of this, if you like. I don't know if that's the right word, but I think you see what I mean. So it alternates. So I'm going to have another branch here. Okay. And I'm going to have another branch up here, which I didn't draw very well at all. Let me just try again. It's a bit better. Now, one thing also that we need to consider is there would be asymptotes at 2 pi and -2 pi. So we also need to introduce asymptotes on the right-hand side and on the left-hand side. Okay. Okay, so the function is not actually defined at -pi and pi, but all the same, we have to put those asymptotes in anyway. Great, so that's the sketch of that. Now, it's going to get confusing, this, but we need to have everything in front of us so that we've got something to play with for the next transformation. So this green graph is y equals cosec of 2x. And our next job is to apply the final transformation. It's got a 0.5 on the outside. All right, so what's the next step? Well, how do we get from that to y equals 0.5 cosec 2x? Well, if we just have a little bit of a chat about this one, the 0.5 is on the outside. So straight away, that's telling us that this is a transformation in the y direction. Okay, and it's as you'd expect. So we have to scale everything by a half again. So again, I'll multiply by half, or 0.5, it's the same thing. So all my y values have to be halved. Now, what's the effect of this? Well, we can cheat a little bit here, because if my y values are being halved, then because it's asymptotic behavior, it's pretty hard to distinguish what a half of 10,000 is and things like that. Because the graph is so steep, it doesn't really, it behaves very similar when you get close to numbers like pi over 2 and -pi over 2, because it's so steep. So what we can do is we can just drag the graph down so that the minimums and the minima and the maxima are half as much as what they were. So if I halve all my y values, what essentially is going to happen is this. If I take this part of the graph here, it's now going to have a minimum at 0.5. Okay, so I'm just going to transfer that there as well. Okay, this is also going to have a minimum at 0.5. Okay, and then half of -1. The maximum is going to be moved up to 0.5. And the same thing here. Okay, so we can now complete the sketch. All right. Okay, so what I've done is I've removed the parent function, the sketch that I copied as a screenshot from GeoGebra, and we've now got the graph sketch of y equals 0.5 cosec 2x. All right, so we'll just label that sketch. So this is y equals 0.5 cosec 2x. And it would be a good idea just to indicate where these minima and maxima are. We're going to talk about that again in a minute. So that's going to be the point 1/2. And this, I'm just running out of room here. That's going to be the point negative 1/2, where these minima and maxima occur. Okay. So for part B, that's what we have to state. So we have to acknowledge that we understand this. So let's write down the coordinates of these maxima and minima. So that's part A, the sketch. Part B, let's do the local minima first. So you're going to have a minimum between negative pi and negative pi over 2. Okay, so right here. And the minimum value is, of course, 1/2. So halfway between those, that's obviously negative 3 pi over 4. And the minimum value is 1/2. So that's the first one. We've also got another minimum occurring halfway between 0 and pi over 2. So that's going to be at pi over 4. And that's also going to be 1/2. Okay, so there's 2 minima in this interval between negative pi and pi. Now we've got some local maxima to consider. So first maximum occurs between negative pi over 2 and 0. So halfway between that, so that's going to be negative pi over 4. And the minimum value is, of course, negative 1/2. Okay, just close that. And we have another maximum over here, the final one. So that's going to be halfway between pi over 2 and pi. So that's going to be 3 pi over 4. And that minimum value is going to, maximum value, sorry, is going to be negative 1/2. Okay, so that's part B. So we've got all those minimum and maximum points that we've just identified all the way along here. So the next point of call is the period of the function. And we have to give our answer in terms of pi. So basically, how often does this function repeat itself? Well, luckily, the way the question is set up, we can see it before our eyes, can't we? It has a repeat pattern. So it's in alternating quadrants. And it's got 2 branches every time it repeats. So for example, if we take the first branch here, so we've got a branch like that and a branch like that, and then the pattern repeats ad infinitum. What is the period? Well, how often does this occur? Well, it's every pi radians. Okay, this occurs. You can see this here because it repeats between 0 and pi. Okay, and then between pi and 2 pi, it's going to repeat again. So the period is really straightforward. We can just write that down now. So for part C, and it does say write it down. Every pi radians, it will repeat. Okay, so we've halved the period because of the contraction by the scale factor 2 in the cosec 2x part. Okay, so I think that concludes worked example 2. So for our final worked example, we've got, again, the parent function cosec x, which I've taken from GeoGebra. I'm just going to label that again. So y equals cosec x, and you get a chance to practice sketching this. Remember, you could start off with the sine graph and then add the asymptotes and then invert from the maxima and minima, and then you've got the shape. We're going from negative 2 pi up to 2 pi. So it's a slightly larger domain this time, from negative 2 pi up to 2 pi, as you can see here. And we have to sketch the graph of y is equal to 1 add 2 cosec x. Right. So let's go through the transformations. First transformation we need to consider is that 2 coefficient there. So multiplying the cosec x. So let's consider how to get to y is equal to 2 cosec x. Well, once again, if you've got a 2 in front of your function, okay, it's on the outside. Using crude language here, but that's basically what we mean. It's on the outside, which means it's affecting the y values. All right, so let's just make a note just to show that we understand what that 2 is doing. So it means we're going to multiply by 2 in the y direction. We're going to double all our y coordinates. Now, because we have this asymptotic behavior on the graphs, it's a good idea just to consider what happens to the maxima and minima, and then you won't really be far off, because once you've got those points correct, you're kind of restricted in how you can sketch the remainder of the curve. So if we look at, let's start on the left-hand side over here at negative 3 pi over 2, 1, which is the minimum. The y value is, of course, 1. So if I double 1, that's going to send my minimum point to 2, isn't it? So it looks pretty straightforward here. Now, also, if we look at this point here at negative pi over 2, we have a maximum at negative pi over 2 and negative 1. And once again, if I double negative 1, that's going to send my maximum to 2. Okay, so let's just overlay this. If we're going to sketch this, we simply have to expand or stretch out our y values. So our minimums and maximums are going to be at negative 1 and 2, at 2 and negative 2 respectively. So I'm going to try and draw that on here. So it's going to come down just similar to what it did before, but it's going to turn around at 2 for that branch. Same thing here. It's going to turn at 2. And the maximums are now going to be at negative 2. So something like that. And it's just nice to have the parent function on there as a guide, isn't it? Okay, now I'll just erase all this stuff I was just talking through. So that's the effect on the curve. So we can say what we've got here is y is equal to 2 cosec x. Okay, notice there's 2 transformations in this. Expect that in your exam. 2 transformations maximum. Okay. Right, and we've got to add 1 to this. Now, if we're adding 1 to our function here, essentially it doesn't matter which way where I put it. If I put it on there, what's going to happen? So if I want to go from this graph to this graph with 1 added, well, clearly I've got to move. I'm using crude language here, but it just makes it intuitive sense. I'm going to move it 1 unit up the entire graph. Okay, add 1 to the y values or everywhere, so the whole graph is going to shift up by 1 unit. So we can do that as well. So I might as well just drag what I've done already and move everything up by 1 unit. So the minimum here is now going to be at 3. Likewise, on this branch here, the minimum is going to be at 3. Okay, and then if I add 1, just be careful here, we're not multiplying by anything, so we've got to move everything up by 1. So it goes back up to negative 1, and here this is going to go back up to negative 1 also. So it looks like we've got our sketch completed. All right, so what I've done now is I've removed the parent function sketch that I took from GeoGebra. We've now got the final sketch of y is equal to 2 cosec x plus 1, or 1 plus 2 cosec x, however you want to describe it. I've just indicated as well where the minimums and maximums occur for each of those branches. So I think we're all set. And the orange lines are, of course, asymptotes, which I strongly recommend you label. Okay, so just to remind yourself of that. Do that, sorry. So these are asymptotes where the graph is not defined. All right. And what do we have to do next? Well, it says write down the coordinates of the points at which the gradient is 0. Okay, gradient is 0. Well, you know from calculus, when the gradient is 0, this, in other words, stationary point. So it could be a maximum, it could be a minimum, it could be an inflection. So can we see any stationary points on here? Well, yes, we can. Just the maxima and the minima, essentially. So there'll be 2 minima there and 2 maxima here. So we have to write down the x coordinates at which they occur. Well, we can do that fairly easily, same as the previous question. So for part B, let's do our minima first. Well, we got the y values sorted out, no problem. So these minima are going to occur when y is equal to 3. So I can add those in straight away. The question is, what are the x coordinates? Well, these are symmetrical, aren't they? So by symmetry, they're halfway between -2 pi and -pi. So halfway between these two values of course, -3 pi over 2. Got a bit tongue-tied then. And also between 0 and pi. So that's going to be pi over 2. Okay, that's the minima sorted out. And we just have to look at the maxima now. It only asks for the x coordinates. I've put those in red. I'm just suggesting that it's easy to see what the y coordinates are. Okay. So the x coordinates, well, it's between 0 and -pi for the first one, for the first maximum. So that's -pi over 2. We'll put that in. Notice the pattern here. And then for the maximum over here, it's between pi and 2 pi. So that's 3 pi over 2. So in answer to the question, the x coordinates are going to be all of these. So we've got -3 pi over 2, pi over 2, -pi over 2, and 3 pi over 2. Okay, it was a write down exercise, but I just wanted to embellish that a little bit based on the sketch. Now for part C, it says deduce the range of values of k for which the equation 1 + 2 cosec x equals k has no solutions. Now I've seen questions like this in parametric equations. It's a nice, interesting question, and just to see if you understand what the graph is telling us. Right, so we're going to do a couple of things. See if you can answer the question. Maybe pause the video, have a think about it, and see if you can find a range of values for k. And then I will go through the solution with you.